Hi. Thank you for the introduction. So, as I say, I'm Roberto Guanciale from the Royal Institute of Technology from Stockholm. You can guess this by looking at my red face after one day in Santa Cruz. So, today I present new attacks that use cache to tamper both integrity and confidentiality of secure software. So, in the last years, there's been a huge investment in formally verified platform, and this paid back by providing hypervisor microkernel, basically low-level execution platform with unprecedented security properties. This platform can be used to bootstrap security of system by giving trustworthy isolation of the critical components and isolating them from less security critical part of the system that can be then implemented using off-the-shelf software. So among this project, there is also Prosper, a project in which I'm involved that focuses on the development and verification of an hypervisor for embedded system. Now, in some cases, this platform has been verified down to the instruction set architecture. So even the binary code of the platform has been formally verified, and so you don't even need to trust the compiler. But even in the state of the art, basically cache are excluded from this analysis. And how much of this is a problem? I mean, we know that cache can affect the execution time of a software, and a detailed analysis of the execution time can be used to leak information from implementation of a crypto service. Similarly, power consumption or temperature can be used and can be analyzed by an attacker to extract information from a secure software. Now, in all these cases, these channels are built over variables that are not part of the formal verification. The main reason is that today it's too difficult to have a formal model that takes into account all these variables. It's really difficult to predict statically the time needed to execute an instruction in a commodity hardware today. But in all these cases, so since these variables are external to the formal model, the software has to use some model external means to counter this attack. For example, you introduce some noise whenever the entrusted software tries to access the system time. But at least the models should be sound, respect the variable that they represent. So if you have a system that has been formally verified down to the instruction set architecture, the formal model used for the analysis should correctly predict the behavior of the software over register and memories. Unfortunately, sometimes this is not the case. So the attack that I will present today uses cache to change the behavior of the software over some of the variable that has been used for formal verification, so they can be used to invalidate the formally verified result. So our attacks are mainly built over incoherent cache behavior. A little bit of background here. So we clearly use cache to speed up memory access. But sometimes some of these memory access should not be cached. A trivial example is when an operating system trying to access some memory-mapped I/O register of a device. So this memory write clearly should not be cached. So today, we configure cacheability of memory using page table and configuring the memory management unit. For each region of virtual memory, we can say if this region is cacheable or not. And this can clearly lead to inconsistency of the configuration. Now we can have two different virtual alias to the same physical address, one that is cacheable and the other one no. This is called mismatched cacheability attribute. So I think there is a difference between here. OK, mismatched cacheability attributes. So we have two different virtual alias, one that is cacheable and the other one no. And if you read the specification of modern CPU, ARM, Intel, Power, the reference manual usually say, don't do this. I would say more, this is, please don't do this. Our secure software shares the hardware with some untrusted component. And possibly this untrusted component is powerful enough to break this assumption. So to configure the system in a way that there are mismatched cacheability attributes over the virtual memory. So if this is the case, you can have incoherent cache behavior. So for example, in ARM, you can have unexpected cache hit. Even if the cache reports an hit during a memory access, the CPU can disregard this cache, this hit, if the virtual alias used is not cacheable. So when an attacker is powerful enough to break this assumption, There are several scenarios today. So one is an operating system that is trying to attack an hypervisor or another operating system. Or this can be an operating system that is trying to attack a secure software that is deployed in some specialized security domain of the CPU, like ARM Trust Zone or Intel SGX. Or this can be a device driver that is trying to attack a user process or a kernel in a microkernel environment. So in all these cases, the attacker, mainly the operating system, is capable of changing the cacheability attribute of its own memory. So I can now finally present the attack. So here we have an attacker and a victim. The victim is implementing a quite common design pattern. So it's a reference monitor. It receives a request from the attacker. It checks this request against some security policy. If this security policy is not satisfied, the request is rejected. Otherwise, it is accepted, and it is used as input for some secure critical function. Additionally, here, we have the parameters of this critical function are passed using memory. So there is a transfer of memory on chip from the attacker to the victim. Initially, both the attacker and the victim share this part of memory, but later on, the victim will remove its mapping, allowing the victim to be the only player capable of accessing this part of memory. So the attacker uses non-cacheable alias. It writes 0 using this virtual memory. This is not cacheable, so we directly write 0 into the memory. We completely bypass the cache, obviously. The victim, for some reason, accesses this region of memory. This can even be induced in a malicious way from the attacker. So it reads the virtual address VA. In this case, this is cacheable. It has a cache miss, so the value 0 is fetched from the memory and is copied into the cache. Initially, clearly, this cache line is not dirty because we didn't change anything into the cache. The attacker is scheduled again, and this time it writes 1 into the non-cacheable alias. So this is not cacheable, so it writes 1 directly into the memory. The cache is completely bypassed. This is an expected cache hit. Neither the cache line or the dirty flag is updated. So the attacker finally transfer the ownership of this memory. It takes its virtual mapping. It removes this, so it frees this part of the memory. And now the victim is the only player that is able to access this region of memory, so should be completely secure to implement the standard reference monitor design pattern. So the victim now checks the request. It reads the request using the cacheable alias, so it accesses the cache. It basically reads 0. It checks this request, this value, against the security policy. Let's say that the policy is D must be 0. In this case, the policy is accepted, so it's satisfied. The request is accepted and not rejected. But now, for some reason, this cache line is evicted. The victim is performing some additional operation over the memory. So this line is removed from the cache. And later on, the victim used this virtual alias again to implement the security policy, the security function. It reads from VA. This time there is a cache miss. We read from the memory. We fetch 1. And basically, the attacker managed to inject 1 as parameter of the critical functionality, bypassing completely the security policy. So this is clearly an integrity threat. And it's based on two facts, and this mismatched cacheability attribute and this transfer of memory on chip. Notice also that between the check of the security policy and the execution of the critical functionality, there was no simultaneous double mapping available for the attacker. So an instruction set architectural model will not predict this behavior of the attacker. So similarly, the same incoherent behavior can be used by an attacker to extract information from a victim. Here, the victim accesses 2 different cache lines dependently on a secret variable. If the variable is 0, the victim accesses the first line. Otherwise, it accesses the second line. There is no shared memory here, but both the attacker and the victim share the cache. And the victim now uses mismatched cacheability attribute over its own memory region to measure if there is some misbehavior of the cache, if the cache is exposing some incoherent behavior. So in this case, the attacker can probe which cache line has been evicted by the victim and discover if the secret variable was 0 or 1. This clearly opens to confidentiality threat and can be used to build access-driven attack where the victim measures the eviction over the cache performed by a victim. So these are not new attacks. In literature, there are several access-driven attacks, mainly to crypto services. But for the first time, you don't need an external variable to measure the eviction from the cache. You don't need to access time. You can just access your own memory to measure if there is an inconsistency in the behavior of the cache. So it's really difficult to counter this attack at probing time because the attacker don't have to access, for example, the system time. So we experiment this attack on some real software. We took our formally verified hypervisor, so in theory there should be no bug here. And this hypervisor has been verified using a quite detailed model of the instruction set of architecture of ARM and implement a virtualization mechanism that is similar to the para-virtualization mechanism of Xen. So we use page table to isolate Linux from hypervisor and the other secure critical components. The page tables are allocated inside the Linux memory, but Linux is prevented to directly write them. So when Linux wants to spawn a new process, it has to write a new page table inside its own writable region of memory. It has to ask the hypervisor, please make this region read-only for me. So the hypervisor change the existing page table so that there is no way for Linux to change this region of memory anymore. That's the transfer of memory ownership, basically. The hypervisor checks that the content of this page table is sound. There is no mapping here that allows Linux to write into another page table or the hypervisor itself. And if this is the case, if the policy is respected, then the hypervisor activates the page table. Now, due to possible incoherent cache behavior, the hypervisor can possibly validate stale data. Now we can have an eviction from the cache. The content of this memory region that is used by the memory management unit is different respect what has been validated by the hypervisor. So Linux can inject a mapping that allows Linux itself to write into the hypervisor memory and take complete control of the system. So for the confidentiality threat, we experiment with AES. So we took an existing implementation of AES. We deployed this implementation inside the trust zone, ARM trust zone. This is a special security domain of ARM that is designed to isolate the critical components from the untrusted operating system. Now, this implementation has no vulnerability. It implements the crypto, the algorithm, using lookup tables. So we exploit an existing vulnerability to measure which cache line are evicted during the encryption. But for the first time, we don't need to access time to measure this eviction. We can just read the eviction by measuring the memory, by reading the memory. So it's really difficult to counter this attack at runtime because the operating system don't have to interact with trust zone service to obtain this information. So some countermeasure. For the integrity threat, you want to guarantee memory coherency. That means that should never happen in the system that you have something in the cache that is different respect what you have in the memory, and the cache is not dirty. You have several strategies here. Either you flush the cache whenever you enter in the critical software, in the critical section. We experiment this in the hypervisor, clearly has a huge overhead, like 800% in the case of the hypervisor. Or you can do something better. You just evict the cache line that you know that can affect the behavior of your software. So this is clearly more efficient, but adds some verification constraint to your system. You need to check that you are actually evicting the right lines. For the confidentiality threat, the standard timing approach can be used. Either you don't use secret-dependent memory access, or if you use a lookup table, this lookup table should be deployed in a region of virtual memory that is not cacheable, so that the crypto service, for example, does not leave a footprint over the cache after the execution. There is also some vector-specific countermeasure. In the case of the hypervisor on Linux, we can force Linux to allocate all the page table in a small region of physical memory, then force also Linux to allocate this region of memory as always cacheable, so that we know that cannot be an incoherent behavior in this region. This clearly requires to change the constraint checked by the hypervisor and change the allocator of Linux. Finally, there are also some hardware countermeasures. I mean, the main reason why we have this channel is that the hardware disregards unexpected cache hit. Just don't disregard them. If there is a cache hit, if there is an expected cache hit, evict from the cache what you don't expect to be there. So some concluding remarks. In the paper, we present also a third attack. This attack uses self-modifying code to exploit incoherency between the instruction cache and data cache and extract information from a PC non-secure application. And some ongoing work. I mean, we discovered this attack by trying to remove some of the assumptions that we did in the formal verification of the hypervisor. So clearly, our long-term goal is to have a general machinery that allows us to repair formal verification performed at the instruction set architecture level. We are also experimenting with some other low-level feature of CPU, like a TLB branch prediction that can be used to build similar channels, similar storage channels. And finally, we are evaluating some hardware countermeasures that can speed up the countermeasure. So thank you for your attention. And do you have any question?
Great, let's congratulate the speaker.
Very nice. I think you did this on, did you try this on an x86 processor? I believe it does detect if you have a cache and uncached at the same time.
So we didn't try with this with x86. So our experimentation has been done only on ARM. So we experimented this with ARM v7, and then we check again, and we have exactly the same behavior also in ARM v8. Okay. Now, in x86, we didn't experiment, but the specification explicitly states that you should not have mismatched cacheability attribute on memory. In this case, the behavior of the CPU can be unpredictable, let's say.
Well, I think you get a machine. I used to work for Intel, so I'll say you get a machine check.
Yeah.
But all those checks are on the L1 cache. If you do a selective flush of the L1, now that's not a CL flush instruction. You actually work the entire set and push everything out.
Yeah.
It won't detect it. So you could have an even more powerful attack here.
Yeah, that's also the case. Yeah.
Great, thanks, Todd.
Hi, David Hartley from Qualcomm. Could you say anything about the interaction between the overrides in cacheability attributes between stage 1 and stage 2 translations in the ARM architecture?
I mean, can you repeat it?
In the ARM architecture, when you have 2 stages of translation,
yes,
you can override the cacheability attributes at stage 1 and stage 2.
So in this case, we experiment with just one stage translation. So in this case, we are a little bit lucky, right? Because with one stage translation, we have complete control of the cacheability in the case of the hypervisor. With 2 stages, even a little bit worse, because the cacheability can be configured in the first stage and second stage. And something becomes cacheable only if both stages say that this address should be cached, right? So in this case, the hypervisor has really no control of what the operating system is doing. And the only way to prevent these mismatched cacheability attributes is to make everything non-cacheable, basically. You cannot force something to be cached by controlling the second stage. You just can force something to be non-cacheable. So the only way for the hypervisor to protect against this scenario is basically to make the whole critical part of memory non-cacheable.
Thank you.
I have a quick question.
Yeah.
You mentioned, so going back to defenses, do you think that having large caches and locking the lines in the cache, is that the way to go for the praise that you mentioned for reference monitors and such? Or are there other alternatives that you would also recommend?
Yeah, I mean, there is always like a balance between like what you can do in hardware, how much this is expensive in hardware, what you can do in software, right? Mm-hmm. I mean, it's important to be aware of this channel. I don't say necessarily that something has to be done in hardware. I mean, removing this unexpected cache hit is something that probably can be done really easily in hardware without like affecting efficiency or like power consumption. It can be, for example, more difficult to keep coherent the instruction cache and data cache. Mm-hmm. So in this case, your formal verification, your secure software should be aware that the architecture does not support this coherency, and you should verify your software against this kind of channel.
I see, and that's why you're trying to unify, you bring this kind of spec into
exactly.
Very nice. Let's thank the speaker once again.